Good afternoon, everybody. My name is Rui Luo, a PhD student at the National University of Singapore. Thank you for joining me at this conference. I'm excited to share our work on structural performance and finite element analysis of 3D printed concrete benches. Okay, let's begin. I will explain why we choose 3D printing in construction, describe manufacturing and testing methods, then discuss our key findings and conclusions. Firstly, I will introduce the background. 3D printing in construction is growing fast because it can create complex shapes and use automation and possibly reduce labor and formwork costs. However, there are challenges. A critical issue is adding steel reinforcement can interrupt the printing process if the rebar clashes with the nozzle or block its path. And the complex shapes can make placing reinforcement more difficult. And another problem is unlike cast-in-place concrete, 3D printed concrete built up in distinct layers that needs extra care to the layer bonding. And there are few studies on the structural performance. So we decided to build a structural 3D printed element rather than just a decorative piece to better understand these issues. We chose benches in park as our test structure for two main reasons. First, they are slender, irregular load-bearing structures at a medium scale, so it's ideal for observing real structural behavior and facilitating tests and optimization. Second, we were inspired by existing bench designs, which allow us to demonstrate the design freedom. Specifically, we want to explore different ways of reinforcing these complex geometries and use finite element modeling to optimize it. Here, we developed three bench prototypes. The first one, bench A, is a baseline design without any steel reinforcement. Bench B uses a 3D printed concrete formwork and filled in with the same concrete. The steel reinforcement had to be placed in the middle. This layout was limited by the assembly method. The third one, bench C, is fully 3D printed concrete with steel reinforcement placed along the lower edge. This one, bench C, is used for practical application on our campus. We put it on our campus. It can comfortably hold two people sitting and one people lying and four people standing. In total, the space of the top only can accommodate up to four people. This example shows the versatility and the functionality. Next, I will introduce our methodologies. This is our material mixture, which we used for both printing and core casting. Then we test the modulus of velocity, compressive strength, and splitting tensile strength following Eurocode. For testing the 3D printed material, we took course from printed specimens. These values shown here are the averages. The first and the second one was quite close, but the splitting tensile strength of 3D printed samples is much lower because we intentionally placed the splitting plane along the layer interfaces. This is how we manufacture the benches. Bench A consists of only 3D printed concrete. This is the simplest and the fastest approach. Bench B here contains more steps. We printed a shell firstly and cured it for 7 days, then add a steel mesh, and then pour the same concrete as the infill. And bench C, we embedded the rebar in real time while printing. Here you can see me, I'm doing this. It needs carefully coordination between printing and the rebar placement. Bench A and C were made more quickly, while bench B involved more steps and 7 days waiting. We tested the benches by placing each of them on the simple supports and applying loads using a hydraulic actuator. We added an extra safety measure to in case the sudden failure, and we recorded the load and displacement data. For bench B and C, we also attached strain gauges to observe stress distribution. And then we built a finite element models to predict stress distribution and the correct development, and to say how to explore how to optimize this structure. In our model, we use the three elements. The concrete is built with solid elements. The intersurface are represented by cohesive elements with the traction separation law, which capture the weaker bond between layers in these layers. And the reinforcement is simulated as truth elements. Specifically, we use CDP model to capture cracks and crushing in concrete and traction separation law to handle the interlayer bonding. The blue data are modified with the test. Then I will show the results. The left one is test and this is the simulation. Bench A developed a single crack early on and which led to a sudden collapse. For bench B, multiple fracture cracks appear and they extended quickly, followed by localized shear cracks in the corner here. And you can see the test here. Bench C has a smoother crack growth drop graph. And the failure mode is the same with bench B, shear crack localization here. As for load deflection relationship, bench A dropped sharply as soon as the main crack formed. It's a typical brittle failure. And bench B and C carry higher loads and greater deflection. For bench B, each sudden drop in this curve corresponding to a formation of vertical cracks. The crack must propagated to the surface of reinforcement. Thus the further propagation of it can be restricted. And for bench C, we don't see this drop because the tensile rebar effectively distributes tensile stress at the lower edge. In both B and C, the reinforcement increases load capacity and the ductility. Bench C shows more efficient reinforcement layout overall. From these results, we can summarize the loading process into three main phases. The elastic phase, everything remains elastic until first crack forms. For bench A, it's also the point of failure is only experienced the first stage. Bench B and C continue to carry the load after cracking because the steel reinforcement controls the development of cracks. In the final stage, the ultimate stage, shear cracks begin to concentrate at the corner. That means the bench is about to lose its capacity. These are data we got from the strain gauge. It's aligned well with the FEM. Then we compared the three benches. Bench A is simplest, but it failed suddenly. Bench B and C got a higher capacity and ductile failure. Bench C requires coordinating between printing and real-time rebar insertion, resulting in moderate forming time, smoother crack propagation, and highest load property. So we think the comparison shows bench C have good trade-off in speed, complexity, and performance. We then did a parametric analysis. We found that reducing section depth or optimizing rebar layout can save materials while still providing enough strength and stiffness. Based on these findings, we set load-bearing targets and balance them with geometry constraints, rebar placement, and manufacturing ability. This led us to an optimized design. We chose the optimized design as we adopt bench C's manufacturing method, but reduced the section height to 60 millimeters. It's 80 millimeters originally. We can say the optimized structure experience is first cracking at about 800 kg. It's a target load, while its maximum load capacity reaches 1,400 kg, providing a comfortable safety margin. Okay, to wrap up, here is our major findings. Reinforcement is very critical. It greatly improves load capacity and ductility. But integrating it into 3D printing should avoid interrupting the printing progress. We found the layer-by-layer integration approach work particularly well for the slender structures like the benches in this research because there's no formwork constraint. And in contrast, formwork first approach can accommodate complex reinforcement cages but require extra space for reinforcement placement, making it more suitable to larger components. Finally, I think the future research could explore hybrid approaches, enable multi-directional reinforcement to further enhance structural performance. Thank you for listening.